Okay, let's continue with our next speaker, Sally and Andrea, that she will answer these interesting questions. What do lines, Fermat surfaces, and Sudoku games have in common? So thank you.
Good afternoon, everyone. It's a pleasure to be here. And thank you, the organizers, for giving me the opportunity to share this work joined with Wallace Mangueira and Jaqueline Rojas. And first of all, I will answer of this question, and the answer is nothing. But this is not a clickbait, okay? This is not a clickbait. I promise that as soon as possible, I will make sense in this title. But first of all, I'd like to introduce the classical problem of counting lines. It's a problem 19th century, and it's to know what is the maximum number of skew lines that a smooth surface in the complex projective space can have. And let's denote this maximum number by LD. And so far it's known that for planes and for quadratic surface we have infinite lines. So this picture helps us to see two families of of lines, infinite lines. For degree 3, what we have, Kale wrote for Salmon, saying that he believed that every cube should have a limit number of lines, and Salmon proved that this number is 27. Another guy who proved this was Klebisch, and he gave this beautiful example, and it's one of more famous. Everybody may know this example and those 27 lines. When we increase the degree, one thing that we should know is that exists a smooth surface that do not contain lines. One example is the surface of degree D, D minus 1, D minus 1, and so for degree D greater or equal than 4, no contain lines. So for the degree 4, Schur found an example who had 64 lines, and 60 years later, Segre gave a proof that the maximum number of lines in the quartic surface should be 64. But 70 years later, Hans and Schut, reading the paper of Segre, saw that he made some mistake in one of these arguments, but the number, it's correct. So they proved and found 64, sorry, 64 lines. Segre should obtain more than 64. And for degree D greater or equal than 5, it's an open question. And what has been done? The mathematicians trying to found upper and lower bounds. Until now, we know that lower bound is 3D squared, 3 by Fermat surface. So we already talk about lines, now Fermat surfaces. And this family is important for us because it's a simple family. We can work on it because we can observe the lines by equations. And we use this technique for solving some problems. About the upper bounds, the first one was given by Klebsch. 80 years later, Segre. 80 years later, Bauer and Hans optimized the Segre's bound. And I hope we didn't need to wait 80 years more to improve this bound, okay? And if you are excited about this problem and you want to work on it, so because it's a simple problem, we can understand, we can explain to a child, but it's difficult to solve. And if you want to read about this and if you want a Portuguese reference, I highly recommend our book. This book was important for us because we stopped to study the lines, these problems, and I know that so far we have seen lines, we have seen Fermat surface, and I need to talk about Sudoku games. But calm down. The problem, another problem related to this classical problem is the problem to counting skew lines. So what is the maximum number of pairwise disjoint lines that a smooth projective surface of degree D can have? The answers of the questions that it's no is for the plane, we don't have any one, and for quadrics, we have infinite skew lines. You can see all the things in this reference. For degree 3, we have 6 by Schlafly, and it's a result well known, so you can see in Hashorn 2. For degree 4, it's 16 by Niculi, and Lira and Rojas prove that the short quartic is an example who get these 16 skew lines. And for the degree 6, Mioka bound given 48 lines, and Ferreira, Lira, and Rojas, studying the family of Boissier and Sarti, prove that the surface of degree 6 in this family contain at least 48 lines. So we have 48. And guess what? SD for D equal 5 or D greater or equal 7, it's unknown. So another problem that you could work on it. And as for the bounds, what we have the Mioka bound, and Hans give an example of a smooth surface of degree D that shows that the degree in Mioka's bound is sharp. And besides the S6, Ferreira, Lira, and Rojas improve the Mioka's bound in the case even, when D is even. Okay, so when we studied those things, we saw this claim of Hans that the Fermat surface contains no family of 3D skew lines. Look, we know about the lines, the number of lines in this family, but we didn't know nothing about the skew lines. So we are sure that Fermat surfaces are crucial for the study of the maximum number of lines and skew lines. And we were intrigued by this claim, and we decided to verify this claim. And there was a mistake. It's a lot of mistakes in this these histories, okay? But it's cool. It's cool. So we proved that if FD is the Fermat surface of degree D, and SFD is the maximum number of skew lines in FD, SFD is equal to 3D for all D except 3 and 5, because for 3, we already know that is 6, and for 5 is 13. Okay. But what about the Sudoku games? Calm down. We are almost there. Let's first understand how works the configuration of lines on Fermat surface, okay? So, our Fermat surface is given by the zero logs of this equation, and we are denoted by phi dfd, the set of lines on Fermat surface, okay? Not so beautiful, this draw, but it's acceptable. And what the technique we use? We made a stratification. So we subdivide this set of lines in 3 disjoint sets. And we name L0, L1, L2. And as I told you before, we can see the lines in this family by its equations. And we have lines here. And we need this index that help us to identify those lines. So we can see that we had D square lines in every subset of this stratification. So the number of the lines in Fermat surface is 3D squared. Problem 1 solved. But we would like to know about the Skew lines. And this is the base proposition that help us construct all the technique we use to count these Skew lines. So these propositions say to us, analyzing relations in the index of these lines when lines in the same subset have intersection, when we choose one here and other here, if they have intersection. So for example, if I take 2 lines in L0, they have intersection if the first coefficient are equal or the second one. So if I want lines, Skew lines, 2 Skew lines here, I need that these coefficients should be different. So we return to this proposition when we play Sudoku. Okay, but we talk about lines on the Fermat surface, and now we are interested to look for Skew lines. And first of all, we look at the number of Skew lines inside of these subsets of stratification. So when we look at these subsets, we can see that we have D, the maximal number is D of Skew lines. And when you look to the union of these subsets, it's 2D. So we get that the maximal number of Skew lines in FD is greater or equal than 2D. It's less or equal than 3D. Okay. For example, the proof of the letter A, the previous proposition, tell us that the maximal number of Skew lines should be less or equal than D, but we can find these families of Skew lines in every subset, so it's D, the number. But, and the Sudoku games. Now I will reveal for you. This is one of the many pages of calculations that we did. We didn't use software, computer, nothing. Just hands and brain and paper, a lot of paper. So what we did, we have the set of the line, we have the stratification, and we look at subsets C of skew lines in FD. And we consider the intersection of C and these subsets of the stratification that we define C0, C1, C2. And using that proposition, we look the relation of these lines. So if we get here in the first subset the maximal number of skew lines, what's happened? Maybe I can choose skew lines in other subsets, and that's really occur. So we studied these things to calculate the things. And in the proposition, you saw that we look at these coefficients, and we look to the sum of the n, congruence modulo d with another coefficient. So this table that we made a Sudoku is for one subset of the stratification, and it's for one case of this relation by the index of the indices of these lines. So I will make an example, maybe two and a half, for you understand how we play Sudoku here. So let's do for the case d equal 3, because it's more simple, because we don't need so many time to make bigger tables, okay? So for degree 3, we solve this. Let C be the set of skew lines in F3, and consider CS the intersection of C and LS for each subset of the stratification. If I choose the maximal number, that is D, in this case 3, here, so if I get 3 skew lines in L0, exists another C, this or this one, that it's empty. So I can take skew lines in the other subset. So we already know that the maximal number of skew lines in a cubic is 6, and we confirm this. So let's play a Sudoku. So I will put the proposition again, and I will write here these tables of the lines. So L0, we have L00, L01, L20, L21, L22. So in the first subset, one, and then não vai caber aqui. Okay, and here L2, okay, let's play our Sudoku game. Let me take another color. So let's start choosing one line in the first set. So let's choose this one. The propositions say to us that if I want a skew line, I can choose lines on this column and this line. So we have these possibilities here. So let's choose this one. Again, the propositions say you can choose here, you can choose here, and the left one is this. So until now, we have L00, L11, L22 on the first strata. Okay, let's go to another set. Remember about these results that if we choose the maximal number of skew lines in one set, here we choose 3, the maximum, on L0. So our C0 was 3. And analyzing the relations, we saw that when we look at the sum of the indexes of these elements, we obtain all the remain of the R3. They remain by the division of 3. So this tells us that we can choose lines on L2. So I wrote this for nothing. So C2, it's empty. And we just can choose here. But looking at this set now, we have to choose lines, skew lines, comparing with this choice. Here, when we look to the proposition, we saw that taking one line in L0 and another one in L1, we should have that the subtraction of the index should not be equal modulo 3 by the first one of this set. So here we have 0, 1 minus 1 will be 0, 2 minus 2, 0. So we eliminate this line. So let's choose this line here. When we look now for the conditions in the letter B, to choose two lines in L1 that are skew lines, we can't choose this column because E should be different than J, and we eliminate when the sum of this index have the same remain. So we eliminate this, and we eliminate this. So let's choose this one. Our rules of Sudoku, we have to block this column, and we eliminated this anti-diagonal and left this line. So we have L10, L11, L12 here. And look, we have 6 skew lines. But maybe you think, but I don't want to do this choice. I want to make different. So be patient when I wrote this. Is for you imagine how hard work we have just writing those things, okay? we have L1, L2, and here it's in the first set. And the second one, I will wait to see how those sets I will eliminate, okay? So let's imagine that we start here, but instead choose this, we choose this one, okay? So here is more simple, it's just eliminate columns and line, and we should get these three, L00, L12, L21. And here we choose the maximal number in this set. And here, when we look at the difference between the indices, we got all the remains possible in the division by 3. So in this case, C0 is 3. And here, the C1 is empty. So we can choose line here. So here, we can keep looking lines here. And for start to choose another line here, we have to see that when we made a sum of these elements, we eliminate this line. And if we start choosing this L102, I can't take another one in this column, and we eliminate these lines here. So we can choose this, eliminate this column, and not diagonal, and we have just this one. So L11 and L12. But the half example is if you didn't choose this one, but choose this, we can't take options here and here. So we just get this plus L21, and in this case, we get 5 skew lines. Here we have 6. So this is the Sudoku-like game that we should work on it. And in fact, we made this type of countings, try to identify patterns and generalize it. But the degree D equal 5, it was the most complicated. It was the last one we found because we are believing that should be 3D, but it wasn't. For the case when D is even, it was more simple. We found an example of families of skew lines who give us 3D skew lines. In the case of D is odd, we have to make so many subcases. So for D equal 3, 5, 7, we have to look for the subset C0, C1, C2 to get the 3D skew lines. And it was a hard work for D equal 11, 2. But finally, we could generalize for the odd case when D is equal to n plus 1, when n are even. This beautiful set of lines give us 3D skew lines. In the other case, when n is odd, we have these other families of skew lines. So if you are interested to play the Sudoku games, you can read our paper, Maximal Number of Skew Lines on Fermat Surfaces, and those are the reference that we use. So that is all. Thank you.